I will be presenting our latest work that we just published at NeurIPS, which is about neural arithmetic. And just from, from the sound of it, it could sound like we just want to teach neural networks arithmetic, right? Which is a bit weird because that's really what they are made of, math. So I just wanted to show this nice picture of a robot learning math. This is not really what we're doing, because neural arithmetic is actually about making neural networks extrapolate better and building more transparent models. And I will go into depth for what both of these words mean during the talk. So I guess I don't really have to introduce people here to what neural networks are, right? They consist of layers that have a weight matrix and a bias vector and some nonlinearity, and then you stack these layers. And the cool thing about these neural networks is that they are universal approximators. So you can see here in the plot, basically black would be the truth and the dashed line would be what the neural network fits in this really simple case, right? It fits it very nicely, but that holds for any function, really. The problem is that they really poorly extrapolate beyond the training range. And they're basically black boxes. So once we've fitted the model, we don't really know, or it's quite hard to tell what it is actually doing. And I think a nice analogy is if you would just want to, or if you would open someone's head and look at someone's brain and you want to tell if they're a good or a bad person, that's basically like trying to find out what a neural network is actually doing or how it's doing its job. Okay, so the first part of the talk will be about the extrapolation part and how we do that in neural arithmetic. And then the second part will be about the black boxness and how we try to fix it. Okay, so again, 3 simple functions. The black part is the true task we want to learn. And then the dashed lines would be what the neural networks learn. And inside the training range, so inside the gray bars, so for the parabola from -1 to 1, they learn it very nicely, but outside the generalization is really bad. And to show you a little preview, so the green dashed bars are now what we can do with neural arithmetic. And you can see that even though we train only inside the training range, we can nicely extrapolate beyond, except for the periodic function on the right, which is something we're still working on, and that's going to be future work. Okay, but how do we do it for parabolas and for the absolute value here? Basically, neural arithmetic assumes that the underlying function that we are trying to learn, or the underlying task, is composed of simple arithmetic operations, so addition, multiplication, and power functions, for example. And then we construct layers that have an inductive bias towards these layers. So basically, each unit represents one or more arithmetic operations. And if the network sees something that's close to this, for example, addition, then it will converge to do addition, and you can perfectly, in an ideal world, extrapolate the task of addition. So yeah, for addition, it's actually really simple. The only thing you need is your input vector x and the weight matrix w. And if you just form a classic scalar product of those two, you basically get you get sums of the input. And if your weights are 1, 0, or -1, you can implement addition and subtraction. For multiplication, it gets a bit more tricky because essentially what you want to do is multiply all your inputs with a weight in the exponent. So if the weight here is 1, then you implement multiplication. And if it's, for example, -1, then you would implement division. And you can already see that as soon as I would input, for example, negative numbers, I would get complex numbers out. And this is really not really what we want, because we are mostly interested in real valued tasks. Okay, so The first neural arithmetic layer that tried to do this was the Neural Arithmetic Logic Unit, published 2 years ago in 2018. And they basically do exactly what I just showed you. They have an addition path that does simple matrix multiplication. And they have a multiplication path that does almost the same as I showed you in the previous slide. And they circumvent this problem with negative inputs by just taking the absolute value. And this basically means that they cannot process negative numbers correctly, right? Because they lose the information of the sign. So that's the first drawback of this solution. And then what this layer does as well, it gates between addition and multiplication. And it turns out that this gating is problematic for converging properly for more difficult tasks. Okay, so as an example, we did a small benchmark. Assume that we want to learn a function with 2 inputs, x and y, and 4 outputs. And the first output would be addition, the second one multiplication, then we have division and the square root. And what happens if we train a classic dense neural network to learn this task on a range, on a training range from 0 to 2? And you can see that in these heat maps here, low values are low error on a logarithmic scale. You can see that the dense network learns the task nicely inside this training range in this box from 0 to 2, but outside it doesn't really generalize well. And then if you do this with the NALU, unfortunately you see that it does not really much better. So it's really like, it also learns it inside the training range, but outside it's pretty bad. So, and this is because it has troubles converging in these more complicated tasks. Okay, and yeah, so then came the next guys earlier this year, 2 guys from Denmark that simplified the NALU and split the 2 paths into an addition and a multiplication path. So addition, again, just matrix multiplication, and in the multiplication path, they now have explicit multiplications instead of this exponential stuff, which means they can nicely represent also multiplications of negative numbers. And it turns out that this approach works way better for the tasks that it was designed for. So again, on the same task, you can see now that the NMU basically learns additional multiplication perfectly, right? Unfortunately though, because it is designed specifically for multiplication, it cannot do any division, not even within the training range. And it can also not do square root. And this is now where we came in, where we tried to solve the other 2 tasks. So basically what we did was taking the multiplication path of the NALU, which is this one, and lifting the whole thing into complex space. Because if we use a complex logarithm and complex weights here, we can easily process also negative numbers, because the complex logarithm is defined for negative numbers as well. And then we just take the real part of this whole thing, because we are interested in real outputs. And then you split basically these 2, and also because we don't really want complex weights in our network, you split the complex weight into the real part and the imaginary part. And then you can do some math to get rid of the complex logarithm as well. So you end up at basically the equation in the top right here. So we have a multiplication equation that looks very similar as before. It has this weight and logarithm of r, which is the absolute value of our inputs. And then we have a bunch of other things that essentially make sure that the sign information is preserved. And this is not like some magic. This basically just falls out of the complex arithmetic that you do. And if you're really interested, I can show you the derivation, but it doesn't really matter. The point is that it works also for negative inputs. And we can also learn arbitrary power functions with this. Problem is that this naive neural power unit, as we call it, also has problems with convergence, similar to the NALU, which is why we introduced a gate in front of the NALU, which eases convergence because it can basically just learn an identity through the whole layer. And that makes it easy to just learn a 1, and then you don't have to propagate through the whole layer, which makes convergence much simpler. And then our result on our benchmark task looks like this. We are not as good as the NMU, but you can see that we are much better than NALU, and we can actually learn all of the tasks, right? So we can also do division, and we can do square root. And just as a reminder, again, this is a logarithmic scale, so the numbers here are actually quite good. Okay, so this is the first part, how to do neural arithmetic and how to do extrapolation on arithmetic tasks. I was kind of planning to just let people ask questions now. I don't know if that makes sense. Otherwise, I would just skip to the next transparent model part. Okay, so I'll just go on. Okay, so we want to do transparent. We want to build transparent models, and our example task for that is to learn a differential equation. And just as a recap, for those who are not that familiar with them, differential equations basically describe change in a dynamical system. So if you have a time series, or a time series like here on the left, which describe actually a classic epidemiological model, then this differential equation describes how from one time step to the next the values change in this time series. Yeah, and the interesting part about this differential equation is that it has a product over here on the right of I and S in its state variables. And it also has these powers, which can be fractional, gamma and kappa. So this is a classic case of where an NPU could really nicely represent this, this differential equation. But what you classically do is you train a neural network, right, to predict these time series, and you basically train a neural network to learn this differential equation if you only have data from the differential equation and you want to predict it. The problem is that even though you can maybe now very nicely predict the course of this epidemic, you haven't really learned anything about the differential equation itself. You don't really know what is happening where and so on. And what you really want as a scientist in order to be able to interpret this problem is the equation itself. So what we did was instead of learning a neural network to represent this differential equation, we just took a stack of NAU and NPU and taught it to learn this differential equation, while at the same time trying to sparsify the whole model. So just regularizing it with classic L1 norm. And then what we end up with is the model you can see here. So the first layer is an NPU, and the second layer is an NAU, this addition unit by the two Danish guys. And what you can see is that if I input my variables S, I, and R, in the first row, the NPU forms a product of S and I. So you can read this very similar to just matrix multiplication, but just with matrix, yes, multiplication, just not with additions between the variables, but multiplications. And then we end up with, yeah, basically this product down here. It also picks out I here, which is then just I. And it picks out basically the square root of R, which is not ideal, but okay, this is just like a proof of concept, let's say. And And then on the left side, you have the NAU, which then of these products that we have formed in the first column here, picks out the correct or forms this addition matrix that you can see in the bottom. So this would be minus beta, this is beta, right? They're almost the same values. And then we have alpha and alpha over here, minus alpha, and the same for eta. So with a really simple training method, we've now essentially recovered an equation that is really close to the truth. And so this is just a proof of concept, I already said. We are not telling you to try to identify epidemiological models just by L1 learning trajectories of what you can download, what data you can download from the internet. This is really just a proof of concept to show that you can theoretically do equation discovery with neural networks and get like an interpretable model out in the end. Okay, so that's already it from me. Our future work will focus on doing this also learning periodic functions, because this is really still a problem we have, but we hope to solve this actually very soon. And then we would like to do some more serious equation discovery than just discovering what a pendulum looks like, for example. Yeah, so, and if you have any applications that you might be interested in, we would be very interested to hear about that, actually. Yeah, so that's it. This was joint work with Tomáš Pevný and Václav Šmídl. If you want to check out our work, here's the link and my email. Thanks a lot.
Thank you a lot, Niklas. We have a couple of questions. Actually, it's a question which you kind of responded, or which you're asking us. So first one, what are the examples of real-world problems where we need to use neural arithmetic? I think one of it, you gave it to us, that we can solve differential equations and kind of predict epidemia, but do you have something else where we can use it?
Yeah, I mean, basically you can use it for any task that is, let's say, inspired by, I don't know, in my case, it would probably be physics or financial modeling, right? Where you have tasks of which you know that they are grounded on mathematics. So for example, we will probably apply them to learning like really complicated magnetic fields of tiny robots, or like stuff like that, where you kind of know that the underlying task is composed of these arithmetic operations.
Mm-hmm. And the second, why did you try, again, it shows that it's POC, so the question is, did you try to solve more complex equations with matrices of higher dimensions?
So matrices of higher dimensions would be like tensors, right? I guess.
Yeah, probably. Mm-hmm.
So this is really like our latest state of the art, let's say. We have a bunch of different directions where we want to try this out, right? And also using this neural arithmetic in larger networks, but we haven't gotten to that yet.